Hello students, our next example is block and string. Till now we have discussed the examples related to linear motion. From this example onwards we will be considering rotational motion as well. So this is the first example. Consider a mass m, this is the mass m, on an end of a string of length r. R is the length of this string on which m is tied to, and it is whirled in free space. So we assume the gravity and friction to be zero. We are whirling this mass along with the string in a free space in a horizontal plane with constant speed v. Now we have to find out what is the force on m. So we are rotating a mass m by keeping the force here. The distance is r, or the length of the string is r. The mass of the body is m. It is moving with a constant speed v. So this is a case of uniform circular motion along a horizontal plane. Okay. Now here we are assuming that there is no gravity or friction exist. So this is a case of a polar motion or planar motion. So we take the two coordinates theta, r, theta and phi. There is no possibility for phi here. So we take r and theta. R is the radial direction. This from towards outside, and theta is the angular direction. It is in the anti-clockwise direction. So the only force, when we rotate this mass m along this circle, the only force on m is the string force, or we call it as tension also. So T is the only force acting on the mass. It is acting towards the center. This is the only force existing which we are giving it to the mass through the string. Okay, this string force is the only force on mass m, which is acting towards the center. So the direction of T is towards the center. So in the case of a radial or the polar coordinate system, the radial acceleration is given by A acceleration A along R, which is read as radial acceleration, that is equal to R double dot minus R theta dot whole square, where theta dot is the angular velocity and AR is positive outwards. The direction of AR is along this direction of R. Now since T is directed towards the origin, we can write the vector T. The force T is equal to minus of TR. So the negative comes from the reason that the T is opposite to R. So when we write this equation in a vector form, if T is a vector, there should be a unit vector along with this. So that unit vector is R, which is in the opposite direction of T. So it is minus this T is the magnitude along with the unit vector R. So this is the equation for the force on the mass m. So the radial equation of motion, we can write it as, we know the equation of motion, F is equal to ma. Likewise in this case we can write the radial equation of motion as the force is minus T, that is equal to m into AR. AR is the radial acceleration, and we substitute RAR like this. Now we are finding out what is AR. So try to find out what is R. R is equal to, in this equation, in this figure we have taken it as capital R, which is the length of that string, which is a constant, which is not changing with respect to time. Therefore R double dot, that is equal to capital R double dot, that is equal to 0. There is no variation of R with respect to time. Okay, so this term is 0. Now what is theta dot? We know that theta dot, which is the angular velocity, is equal to V by R. We know the relation earlier. So we were calling it the relation as omega. Omega is equal to V by R. Omega is actually this term itself, the angular velocity. Theta dot is equal to V by R. Therefore we obtain AR is equal to, this term is 0 minus small r is equal to capital R. Theta dot is V by R square. So this equation becomes minus V square by R. So AR, the radial acceleration, is equal to minus V square by R, or T is equal to, when we substitute AR in this relation, you get T is equal to mv square by R. So m is the mass of the body, v is the orbital velocity, and r is the radius or the length of the string. This is the equation of motion, or we have to find out the force on the mass m. So the force is T is equal to mv square by r. This is our relation. Now note that T is directed towards the origin. Okay. T is the force on the mass m which is directed towards the origin, and there is no outward force on mass m. Okay. Now if we whirl a pebble at the end of a string, you feel an outward force, right? When we start whirling a pebble at an end of a string, you feel a force towards outside direction. However, this force you feel does not act on the pebble, it acts on you. It acts on the hand on which this rotation is taking place. This force is equal in magnitude and opposite in direction to the force with which you pull the pebble. Okay, assume that a string's mass is negligible. So that is the force which is equal and opposite to the force with which we pull the pebble. So there will be always an equal and opposite force existing along with this. So that is the force which we feel in the outward direction. Okay.